Plastic cable.
Audio test 1 2 1 2. I'm going to leave the microphone on.
This isn't WebEx, is it? This begins EE 483 on Wednesday, July 9th, 2014.
Pero tranquilo, Yulai. Chingando un café para el frío. Me vamos un chingo de calostro. ¿En dónde están, chavos? ¿En dónde están? ¿En tu cuarto? O en el cuarto de los shift-invariant. ¿Qué pasa? ¿Cómo se ha comportado el bebé? Deberían de ver todo lo que le compraron al bebé. Bueno, tampoco le compraron tantísimo, pero pues sí le compraron algodón. Le compraron pues un montón de pañalito, cajetos. De 9. ¿Qué fue eso? ¿Qué figuritas de...?
tonight is very interesting in that we don't have any assignments due tonight. So that's nice. Okay. Let's see. Yeah, sorry about that. So knock that one in. Okay, now there's something else. Oh, yeah. I did, no, I shouldn't say that. Let me say it correctly. I didn't go through the projects. I'm having the graders looking them over, but I'll go over them a second time and assign the final grade. So the bad news is I don't have them, but the good news is if I go through them, you probably get a higher grade. So there's nothing wrong with that. I did, as I talked to a student before class, I did briefly scan through the projects. I have to say I was it was amazing because I got a lot of good questions on the projects. And it looks like most people got the main idea, did a good job. So anyway, okay, so tonight we will continue our we will continue our stroll down sampling lane, and hopefully can cover the basics of that. I will have a second project, but I'm not sure yet. I haven't made it yet, so I'm not sure if it'll be on spectrum analysis or something to do with sampling. We'll see. We'll see how it goes. In any case, I'm sure you don't mind a little break from. Okay, if you. Oh, you did. Strange. Okay, so I might as well get started. Can you see this? I don't know. Hey, should they turn off the light? Maybe. Okay, great. Oh, yeah, I see what you're saying. Yeah, that's not too bad, I guess. So anyway, well, all right, so tonight, as I said, we will continue the discussion of sampling. And last time we covered really two important theorems that relate to sampling. One theorem was it was what we call the frequency domain version of the sampling theorem, but actually, okay, where was it? Frequency, but actually the frequency domain version of the sampling theorem was a little more general in some ways than the time domain version. And I say that because we introduced the concept of aliasing last time. And aliasing had to do with, as you recall, if the bandwidth of the continuous time signal was too large. And by too large, I'll see, no, it's a little bit ahead. By too large, oh yeah, here it was. By too large, I meant that the bandwidth of the continuous time signal before sampling, if it was greater than half the sampling rate, or if in radians per second that bandwidth was greater than pi over t, where t is the sampling interval, then we have problems. We have what is called aliasing. And on the other hand, if the bandwidth is less than half the sample frequency, as we discussed, then we have no aliasing. And in fact, we can recover, or through interpolation, we can actually recover the continuous time signal if we wanted to. Now tonight I'm going to talk about a kind of an application of this in terms of what if we didn't want to recover the continuous time signal, but we wanted to essentially resample the continuous time signal at a higher rate without having to reprocess it through the A to D. In other words, we sample the continuous time signal at some rate, and then all digitally we resample it to any rate we want. Well, not any rate, but a wide class of rates. So we'll talk about that tonight. But the point I want to make, though, is that the sampling theorem in the frequency domain version actually applies if there's aliasing or if there isn't. Regardless of whatever condition we have, we always have this relationship between the DTFT of the sampled signal and the CFT of the continuous time signal. And the only thing is, if there is aliasing and the bandwidth of the continuous time signal is too large, exceeds exceeds the sample frequency divided by 2, then you see all these images, they will overlap each other. So what we've shown through the frequency domain version is when you sample the continuous time input, then in the frequency domain, the DTFT of the sample signal is really a superposition of the continuous Fourier transforms, and in the superposition, the copies of the continuous time Fourier transform are separated by intervals of 2 pi over t. So there can be aliasing, there doesn't have to be aliasing. Either way, this frequency domain sampling theorem does work. Now, in the time domain version of the sampling theorem, there we actually restricted our attention to the case where, this is the Nyquist or aliasing condition, etc. we talked about. In the time domain version of the sampling theorem, there we really restricted our attention to cases where there was no aliasing. And what we found was that if there is no aliasing, in other words, if the bandwidth of the input signal is less than half the sample frequency, then what the time domain version of the sampling theorem shows is that, yeah, we can reconstruct exactly the continuous time waveform from its samples, x of n. Okay? But that's only if this condition holds, no aliasing, see? Whereas the frequency domain version works for aliasing or not. So those were the two important results that we discussed last time. And then we started to talk about an example. Now, I did want to point out, so we talked about a sine wave example. I do want to mention one thing, though. If you look at see example 4.1 if you have the third edition of Mitra, or because he covers cases just like this, or example, what is it, 3.18, look like 3.18 in fourth edition. So Mitra. So Mitra does cover some sine wave type examples. I think, as I indicated, wait a minute, this one is 2. Okay. Oh, I see, yeah. As I indicated last time, sine wave examples are nice because it's an example of a continuous time waveform such that it is perfectly band limited. In fact, as I mentioned last time, the continuous Fourier transform of the sine wave looks like this. I think I mentioned that. Oh yeah, there's where I mentioned it. But here, if I were to draw this, f, and then versus x of f, in the continuous time, x, I should say x sub c of f, I would find there would be a spike here at f naught, and a spike over here at minus f naught. But it would be perfectly band limited. So as long as f naught was less than fs over 2, then, you know, you wouldn't have any aliasing. So the sine wave is a very nice example to look at in terms of sampling. And we did that last time, or we started. I just want to say a few more words about it. We looked at two cases, or we were looking at one case. I'll look at the second case tonight. One where there's no aliasing. That was the case of where we had 4 samples per period, or equivalently, we sampled the sine wave at 400 hertz, but the maximum bandwidth was limited to 100 hertz. So clearly no aliasing for this case 1. And what we discussed, or as we discussed, that in this case, as it turns out, we could, well, wherever it was, we could expect to sample the sine wave with no aliasing. And in fact, if we looked at, this is what I drew just a second ago for the continuous, the Fourier transform of the continuous sine wave. If I were to draw, now, and recall, x of n is equal to cosine 2 pi f naught nt, where again 1 over t is there it is 400 hertz, f naught is 100 hertz, and if I were to draw the spectrum of x of e to the j omega, of course it would be periodic, but as a function of omega, let's draw the first period between pi and minus pi, and guess what we would see? We would once again see two spikes here and here, so it would look very similar in shape. The only difference would be, so there would be two, and these will both be Dirac delta functions. The only difference would be that this occurs at omega naught minus omega naught, where omega naught is equal to 2 pi f naught divided by f sub s. Where do I get that? That comes right out of the sampling theorem. If you look at the sampling theorem, in fact, the frequency domain version of the sampling theorem, you see that somewhere in there, is this it? Frequency domain version of the sampling. Oh, yeah, I think it's somewhere here, just to show you. So, yeah, here it is. It's omega over t, which is equal to omega times fs, and that maps to big omega in the continuous CFT domain. So that if we set omega naught equals 2 pi f naught, then this maps into little omega naught times fs, where omega naught is equal to 2 pi f naught over fs. So the frequency, or in the DTFT, where it shows up, does depend now, because we're sampling a continuous time sine wave, it does relate directly to the analog frequency, or the continuous time frequency, f naught in hertz, of the continuous time sine wave. Okay, and the mapping between frequencies in the discrete time DTFT domain, the little omega and the big omega, or f naught, that mapping is done through the frequency domain version of the sampling theorem. So very, very important to go through this, make sure you understand what we had derived. And like I said, I like the frequency domain version. It is more general. Okay, and I'll mention that a little bit more in a second. So anyway, that was the case one. And, you know, two spikes in the frequency domain, two spikes in the discrete time DTFT domain, and the spikes were located at the frequencies you would expect, namely omega naught equal 2 pi f naught fs. So there's a direct mapping here, but that's no aliasing. Now, in the second case I took that we didn't have time to go through was, in this case, I assumed that fs, this is where I was going to start. Yeah, so in the second case I was going to discuss, before we ran out of time last week, was when we undersample the continuous time sine wave. So in this case, we still have f naught equals 100 hertz, but we're going to use an fs of 150 hertz. So definitely we have aliasing in this case, aliasing. So, and aliasing, well, we know that when I wrote out the frequency domain version, you get overlap of images. But let's see what that looks like for a sine wave. In fact, it's very, very interesting what happens when you undersample a sine wave. So for this case, here's our sine wave. It's not artist's rendition, pretty bad. But we're going to sample this at very, very sparse points in time. And again, this is not a great diagram, but basically we're going to sample it, say we sampled it at t equals 0, then we're going to sample it way over here. We're not even going to, see, before we sampled it here, 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 here. We're going to miss all these points, and sample it here will be our next sample. And then we're going to miss all the points in the middle and sample it over here, and so on and so on. So we're really, really sampling at sparsely spaced points in time. So I ask you, what do you think the sampled signal would look like? And, you know, you look at this, it's kind of not obvious to see what it would look like. Namely, I'm going to ask, do you think if you sampled at these points in time, for example, would the sampled sine wave, would it be periodic? Would it look anything like this since we're doing aliasing? Well, let's take a look. So in this particular case, if our period is, t period is, well, I wrote it down here. T period works out to be 2/3 of 1 over f naught for this particular example. No, I'm sorry. T period is 1 over f naught, sorry. You're sampling it, though, if you sample at 150 hertz, that works out to be exactly 2/3 of t sub period. Flip it over, and 1 over t period is 100 times 3/2 is the 150, okay? So I'm just relating the sampling interval to the period of the sine wave. 1 over that gives you the 150 hertz for this, and again 100 hertz for the sine wave. Okay, so we know this. We have this, that Fs is 150 hertz. F max is 100 hertz, so that's greater than Fs over 2, and again, for the nth time, aliasing. Okay? Now, you'll see why I like the sine wave example, because it's actually, this thing's almost trivial to analyze. But I'm going to make a little substitution here in just a moment, which always catches people off guard, even though it's just a sine wave. Okay, so here is my x of n. X sub c of nt, which is, once again, cosine 2 pi f naught nt. Okay, now, but f naught times t, okay, this two terms here, that's going to be 1 over t period times 2/3. That's going to be 2/3, dimensionless, okay, as we would expect. So now we have that x of n is cosine 2 pi times 2/3 of n. Okay, now I'm going to do a little substitution. It looks trivial. It always catches people off guard. What I'm going to do is, instead of 2 pi times 2/3, and I'm doing this to make a point, I'm going to rewrite this as 2 pi n. Basically, this is 2 pi minus, well, here, I'll even write it like this. 2 pi times 1 minus 2/3 times n. So this is what the cosine is, but I've written it in this form. Now, my first question to you is, well, this is always confusing. Why did I do that? You'll see in a second. But the first question I ask you, are these two, in fact, the same? Aren't they, or I should say, aren't these two the same? This cosine 2 pi 2/3 of n and cosine 2 pi n minus 2 pi times 2/3 of n. Yes, they are the same, obviously, because cosine of 2 pi, any integer, minus x is always equal to cosine of minus x, right? I've just added 2 pi into this, which is equal to cosine of x. See? So it turns, all I'm doing is adding, I'm inverting this, or I'm taking the negative of this, because cosine of minus x is the same as cosine x. So I'm taking the minus, and then I'm adding 2 pi, multiples of 2 pi, okay? So these two are, in fact, the same. But now let's take a look at this argument. It's 2 pi times 1 minus 2/3 n. So the reason why I went through this is that if you look at this, 2 pi times 2/3, what is 2 pi times 2? See, this is what we've been calling omega naught, right? Okay, but I like to keep omega naught between pi and minus pi because everything's periodic outside of that. But what is this? This omega naught is equal to 4/3 of pi. And that's greater than pi, okay? So I don't like that. I want to keep everything between minus pi and pi because I know it's going to be periodic outside of that. So that's what all of this stuff was about. It was just adding or subtracting multiples of 2 pi so that I would end up with an expression that I'm more familiar with. Cosine 2 pi 1/3 to n. Now sometimes the students get confused and say, okay, so you've replaced this sine wave with this. They're the same. They're the same sine waves. But multiples of 2 pi n doesn't change the sine waves. These are the same. But in this representation, now your omega naught is equal to 2 pi over 3, less than pi. So I like that. Okay, I like that. I've got that into that form. But yes, you will see multiples of that in the frequency domain. You will see this frequency and then that plus 2 pi, etc., because the DTFT is periodic. Okay, well, I'm just going to express that as 2 pi f naught prime times nt. Now, where f naught prime times t is 1/3. Now, if I were to ask you, like if you recall before, I said that this frequency, when we did the first case without aliasing, I would find, in the frequency domain, I would get 2 spikes at omega naught and minus omega. Little omega naught is in units of radians, not per second or anything. But the little omega naught is related to the true, if there's no aliasing, it's related to the true frequency, which is in hertz, by this relationship. Or if you want to look at omega naught over 2 pi, that's equal to just f naught over fs. Okay, either way you want to look at it. But if you want to ask, okay, I've got a signal, I didn't alias, and I'm looking at it, I'm getting frequencies here, what do they correspond to? Because I sampled a continuous time waveform. What do those frequencies correspond to in terms of the continuous time world? Well, it falls right out from the frequency domain version of the sampling theorem, and this is the relationship. So if you want to know what a little omega naught represents in the continuous time world, just multiply omega naught divided by 2 pi by the sample frequency, and that's it, see? Okay? So, let's try that over here. So here is our f naught prime times t, in this case, is equal to 1/3. So in this case, omega naught, we would say, is equal to, what did I say up there? 2 pi over 3, which I'm saying is equal to 2 pi f naught over fs. And cancel, that implies that f naught is equal to 50 hertz? 50 hertz? Whoa. Oh, that's strange. So what this is saying is that, well, if it could talk, I guess I'm saying, but if it could talk, what it's saying is, you know what? I just sampled a sine wave at 150 hertz, but I aliased. So, you know, really, if you're just looking at the samples, you can't tell whether I sampled a sine wave at 150 hertz or I sampled a sine wave at 50 hertz. If the sine wave were at 50 hertz, remember, in this second case I'm sampling at 150, we wouldn't have had aliasing. But what this is saying is that, but if the sine wave is at 150 hertz, it's going to look just like it was, or it's going to look just like a sine wave at 50 hertz would look like. So that is the problem of aliasing. So when we sample a 100 hertz cosine wave, I guess it's not 150 hertz. The frequency was 100 hertz. At 150 hertz, it is equivalent to sampling a 50 hertz sine wave, also at 150 hertz, because of aliasing, see? So that's what aliasing does, and it's like my friend pointed out last time. It's like the looking at a carriage with the spokes. You watch it on TV, and it looks weird. I mean, it looks like the spokes are going backwards or they're going very slow. It's because you're looking at that through the camera. The camera typically takes 20, 30 frames per second. The wheel is going around much faster, and so what you're going to see to your eye is kind of the equivalent of this aliasing condition. In this case, it made a 100 hertz sine wave look like 50 hertz. Now the question is, you think about that, well, that's kind of interesting. Is there some way to tell? If I give you a sine wave at X frequency and I've deliberately aliased, is there some way to tell where that frequency is going to end up when you sample it with aliasing? And the answer is sure. Sure there is. And the key is, once again, for the 10th time, the frequency domain version of the sampling theorem, see? What the frequency domain version of the sampling theorem says is that when you sample a continuous waveform in the DTFT domain, you will get images, and they're separated by 2 pi over t, or in hertz, that's by Fs, okay? So when you sample this sine wave at 150 hertz, you're going to generate copies at every multiple of 100 hertz. Okay, so you're going to generate copies at 150, 150 minus 100, 150 minus 200. Oh, I'm sorry. Oh, Jesus. I think, what am I? Got to get more sleep next time. I'm sorry. The sine wave frequency is 100 hertz. So you're going to generate copies of that at 100 hertz. 100 hertz minus 150 hertz. 100 hertz minus 300 hertz, etc. Multiples. And remember, this is a real sine wave, so there's also a component at minus 100 hertz, right? I drew that, minus F naught. So that's going to be generating frequencies at minus 100 hertz, minus 100 hertz plus 150. What's that? 50 hertz. So it's all of that overlapping. In this case, there's so much overlapping that these high frequencies are looking like small frequencies. I have attempted, not a great sketch, but I've attempted to do that here. It's a little rough, but let's look in the frequency domain. So here again is our cosine wave at 100 hertz. F naught in this case is 100 hertz. But here's what happens in the DTFT domain when you sample it at 150 hertz in this example. And I've tried to draw all the images, but what you would find is when you do the frequency domain version of the sampling theorem, you add all these images up. And remember, each copy, X sub c, it only has 2 components. So this is one you could actually do almost by hand or graphically, and that's what I tried to do. So I got when I did all that, I got the solid lines are just the image with n equals 0. Okay, you get an infinite amount of images, and they're just copies of the continuous Fourier transform, but displaced by multiples of 2 pi over t. Okay, so look at the n equals 0 term. That you get the solid curves here. That's the n equals 0. Okay, and then I drew for you the n equal 1 term. You will get, where is it? You'll get the dash. See this dash line here? It turns out to be at minus 50 hertz. And then the n equal 1 term, because of the negative image, will also be frequency, I don't know, minus, I can't even read that. But anyway, at separated by. So one would be at 150, and then one would be at maybe minus 150. It's basically, what is the separation here? This is 100 minus 1, it's 200 hertz. So this is going to be at minus 50, and this will be at minus 250 separated. But in any case, these two dash curves with the little n equal 1, that's the n equal 1 term. And it does show up at minus 50 hertz. The n equal minus 1 term shows up at 50 hertz plus 250 hertz, I believe. I think that's 250 hertz. So, yeah, 10 pi over 3, whatever that is. Okay, so then the dash curves are this, and at n equal minus 1 give you this, n equal plus 1 give you these two terms. So if you look at this between minus pi and pi, just cut out the interval, minus pi and pi, and keep in mind this will all be periodic. You can sketch that out yourself. But if you're just looking at minus pi to pi, guess what you see? You see spikes at plus 50 and minus 50. Okay, and those come about from these images at n equal 1 and n equal minus 1. So if you're looking at the D, and then you'll know it repeats outside of that. So if you're looking at the DTFT between minus pi and pi, you look at it, and you realize you're getting a frequency component in radians at 2 pi over 3, which for that sample rate will map back to 50 hertz. So it's very hard to tell. You can do this in the frequency domain. I kind of like the time domain for this because in the time domain, manipulating the cosine is a little bit simpler, like doing these kind of tricks. But however you cut it, you won't get what you think that you've sampled. What you will end up seeing for this case, in fact, for all cases where you undersample or where there's aliasing, you will actually see frequencies that you think are much lower than they really are in the continuous time world. So very, very interesting in terms of the sine wave. Again, the summary is if you look between minus pi and pi, you will get in the DTFT, you will get spikes at plus or minus 2 pi over 3, which once again correspond in the continuous time world to the frequencies plus or minus 50. So that is aliasing. Okay, now we've covered, that covers pretty much the basic theorem, the frequency domain, the time domain versions of the sampling theorem. In many cases, I think actually the frequency domain is more illustrative because especially if the spectra is pretty simple, you can tell right off the bat by looking at those images in the frequency domain whether you're going to get aliasing or not. The time domain version only applies if there is no aliasing. So, now what I want to talk about is, I kind of want to talk about an application of the sampling theorem. In the time domain, we saw, though I won't repeat it again, but we saw that we could recover the continuous time waveform from samples of the discrete time sampled signal using these sync functions as long as there is no aliasing. So it's, I'm sorry about this. Just one more time. One more time. I promise this is the last time I'll... This, by the way, what I'm doing right now, okay, what you see me doing, I think, drive students up the wall. So I've tried to minimize, when I try to go back, just to repeat an equation. But in any case, as I'm doing now, but in any case, okay, we saw this. If there is no aliasing, we have this result. We can recover the continuous time waveform. So what I'm going to do, essentially, is I'm going to say, well, look, I don't want to regenerate the continuous time waveform. In fact, it's not even practical, really, because you need these sync functions and infinite, absolutely convergent, it's not, and all that kind of stuff. But what I really want to do, instead of generating the continuous time, I want to let t equal, so you're sampling at instance x of n equal x sub c of nt. Okay, I want to resample this at the instances, say, n times t over L. Say, where L's a nice integer. In other words, I want to basically resample my continuous time waveform at instances which are much more closely spaced in time than what I sampled it before. This would correspond to a new sample frequency. I'll call it Fs prime of L times Fs, because the interval between the sampling points is much smaller. So I would like to do that. Well, you look at this and say, now, first question first, you haven't aliased. No, I haven't aliased. Okay. Well, then I suppose we could just substitute in here t equal, what do we say, n times t over L. So we could let t be n times t over L. You would get it here and here. And what you would start to realize is, hey, you know what? You know what? Maybe I don't have to build a second A to D converter which samples at a faster rate. I might be able to effectively resample my signal by using the samples I had. You know, do the whole thing digitally. So I don't even have to think about going back to a different A to D converter. I can use the time domain version of the sampling theorem. So that's what I want to talk about. And the basic idea, oh, well, first of all, just a quick note, some examples. We'll talk about both upsampling, where I sample at a new interval, which is the old interval over L, where L is greater than or equal to 2, typically. I mean, it's not 1. That would be the same thing. That is upsampling. Downsampling is, that's pretty simple. That's just t prime equals L times t. The interesting thing is that, I always find this, in the frequency domain, as we will see in a little bit, in the frequency domain, this is actually much easier to represent the DTFT of the upsampled signal vis-a-vis the DTFT of the originally sampled signal, whereas in the time domain, this is a little bit more tricky to represent. This is very simple to represent in the time domain, but it's a little bit trickier in the frequency domain, so we'll see that. And there's a lot of applications for this. A lot of times we sample the input at some frequency, but we then maybe go through some nonlinear DSP. Nonlinear DSP could be timing recovery if it's a communications system, could be a lot of things. And in the nonlinear digital signal processing, if you don't change the sampling rate, you'll get a lot of images and harmonics, etc. And so a lot of times before you do this nonlinear DSP to recover timing or whatever you're doing, you would like to upsample the signal to effectively generate samples much more closely spaced. And that's would be one application of upsampling. You would go through some nonlinear DSP, and then that would provide a timing pulse, a very nice timing pulse to sample your original signal. So that could be one example. Lots of examples of downsampling. Downsampling happens if you realize that you've oversampled your signal and you want to do a lot of DSP at a slower sampling rate because it's easier to implement. So that would be an example of downsampling. Like here's a case where, for instance, suppose you're, as an example of downsampling, suppose your continuous time spectrum looks something like this. It has a signal that's maybe some small bandwidth, but then out here at a very high frequency, there is an interferer, see? So you would want to make sure you sample this fast enough. Why? Because if you, so you might say, hey, wait, let's say this is, I don't know, let's say this is 100 kilohertz, I'm just, some number. You would say, oh, well, most of the energy is down below 100 kilohertz. I know there's this interferer up here, maybe it's a megahertz, I know this interference is up there. But I just want to look at this. So you know what? I'm going to sample this, a sample rate of 200 kilohertz. No problem. There's no aliasing of the signal. You know what, though? Guess what? This interfere at 1 megahertz, you're going to see copies of that, as you recall, separated basically by the 200 kilohertz. So you're going to see a copy of this at 800 kilohertz, 600 kilohertz, 400, 200, 0, or wherever its frequency is. So after you get done sampling, you do your DTFT, guess what? X of e to the j omega pi minus pi. Yeah, you're going to see your signal. It's going to be there, but guess what? Interfere is going to alias into your band, okay? So that's an example where the interfere aliases into your band. But what you can do in a case like that, so you're kind of stuck. You can't sample this at twice the bandwidth of the signal. You really, unless you like aliasing of this interfere, you have to really sample it at, in this case, 2 megahertz. See, Fs equals 2 megahertz. But now you know that that is way too high to process most of the signal. So this is a perfect application of downsampling. You would go into downsampling. What the downsampling is, we will see, is it first filters this digitally filters the signal to get rid of this interfere. Now, after you've sampled, then you're okay. Then you will see the signal here, and you will see the interfere at the higher frequency without aliasing, okay? So you will see both. Then what you will do is filter the input signal, and then you downsample it. Then you can do your rest of the DSP on the lower rate signal spectrum itself. And we'll talk about ways of doing that efficiently. So a lot of good stuff with upsampling and downsampling. And by the way, in MATLAB has a neat function called resample. Okay, resample. It's called y is equal to resample. X is your input signal, and like, for instance, n, comma, m. And what that does is resamples basically from, let's see, let me make sure I get this right, n over m. Yeah, from t to t prime equals n over m times t, okay? So MATLAB, that's all built in. It's a simple function to use. And if you haven't used it, you will find this is a very good function to use if you're processing, especially if you're processing recorded data. This is very, very important. And it's used for applications like this, as I was talking about, or for this, for upsampling in nonlinear DSP. Any case, anywho. So I want, as I said, I want to talk about digital ways of resampling the signal. Basically, what MATLAB does. You know, it's here we go. Beg your indulgence. So I want to talk now about exactly the math behind what the MATLAB function is doing. And this is exactly what the MATLAB function is doing, okay? So once again, we have x of n is equal to x sub c of n times t, and then we want to create a new signal, x sub I of n equal x sub c. This is going to, first we'll talk about upsampling, okay, then we'll talk about downsampling. So we want to create a new signal that's generated from n t over L, all in the digital domain. We don't want to go back out to the continuous time world. We want this to, so basically we want to take our samples and come up with this handy-dandy, snappy way of taking x of n and going through a filter or something and generate this x sub I of n. I, by the way, is just interpolation. Okay, so we're going to again assume that there's no aliasing with the original sample rate, so we will assume that the original omega max, so no aliasing with sampling at f sub s equals 1 over t. Okay? So there will be no aliasing. So what that implies is that omega max we will assume is less than pi over t, or in terms of, that's in radians per second, or in terms of hertz, we will assume that the maximum bandwidth of the continuous time signal is less than our sample rate. Okay, so that's just for starters. Just for starters, we're going to assume that. And again, the name of the game is how do we generate a resampled version all in the digital domain. Okay, and if we look at, okay, given that there is no aliasing, what we find is that this x of e to the j, I'm just summarizing this equation, I can't hardly read it, x of e to the j omega is equal to, now check it out, 1 over t, okay, times x sub c, that's continuous time Fourier transform of little omega normalized by 1 over t. Okay, so you might say, where's the infinite sum? Let me finish writing. Minus pi less than omega less than pi. Or maybe it's less than or equal. Okay, so what I'm claiming is in that interval, if there is no aliasing, that's exactly what the DTFT looks like. In fact, it's exactly a scaled 1 over t amplitude scale and frequency scale version of the continuous Fourier transform. Again, no aliasing, okay? So no aliasing. And then, in fact, that corresponds to the 0th image. Okay, that's that term. Here's the, it's hard to read that, but anyway, here is the full solution. And it's there's the copies, and for the term 2 pi k over t, for k equals 0, you get exactly that, since I'm assuming no aliasing. And then you just, outside of this interval, it just repeats, okay? The interval, pi to 3 pi is the next term in that sum. But there's no overlap, so that's nice. So here is our pretty little picture of this. So there is our picture. And this, again, is the DTFT. Again, my apologies, but make sure I don't miss any points. This would be the k equals 0 term. In pi, you would have another image looking like this. I'm assuming triangles here. This would go to 3 pi. Bingo, bingo. That would go to 5 pi, etc., etc. And this would be the k equal 1 image, k equal 2, and so on. And you get the negative images too. K equal minus 1, etc. K equal minus 2. So that is what your DTFT would look like if there's no aliasing. But right in this interval, your DTFT is just a scaled and frequency scaled version of the continuous or the continuous transform of the continuous time signal. Now, let's suppose we sample x sub c of t. Now, keep in mind where I'm going. Where I'm going ultimately is I want to show you how to generate this resampled version directly from the samples. But before we go that far, let's take baby steps in doing that. So the first place I'm going to ask you is, forget about resampling and all that. Let's suppose that I sampled x sub c of t at t prime equals t over L. Or as I said, fs prime is equal to L times fs. I'm just sampling. I am resampling. I'm sampling the continuous waveform with a much faster A to D converter. So what are things going to look at? First, another sketch of the CFT. Okay, now this is the, see, I'm switching back and forth. This was the DTFT, and now I'm going to look at the CFT. Okay, so really there is no sampling at this point. This is just the one pulse. But I'm trying to show you what does this look like when I do sample it at the higher rate. Well, it would look like this. This omega max is pi over t, as I said. And this mega max is, well, I'm sorry. I'm assuming omega max goes right up to the edge. So we want omega max to be less than or equal to pi over t. So I'm showing it going right up to pi over t, okay? Now also on this graph, I will superimpose the new sampling frequency. That new sampling frequency is pi over t prime, see? Where again, t prime is t over L. So when we do sample this at t prime equal t over L, or fs prime equal L times fs, we're going to repeat images of this every fs prime frequency, okay? So I'm just showing where that frequency would occur. So the pi over t frequency, that's what we originally sampled it at, occurs right here. I'm going to assume that you just have no aliasing. It occurs right at the band edge. But the new sampling frequency, or this higher sampling rate, I'm assuming it occurs way out here, okay? So bottom line is, if you have no aliasing with the original sample frequency, you're definitely going to have no aliasing with the new sample frequency since it's higher. Fs prime is definitely much greater, depending on L, than F max, see? So, or F max over 2. So definitely no aliasing. Note that F max is equal to Fs over 2. Omega max over 2 pi is equal to Fs over 2, which is much less than Fs prime over 2. So now there is plenty of room to avoid aliasing. I guess that was my bottom line. So note that the frequency, pi over t prime, corresponds to the new Nyquist frequency, Fs prime over 2, okay? So I'm just saying pi, I'm just repeating what I said. Map corresponds to Fs prime over 2, which is L times Fs over 2, okay? Okay, so now we're going to take a DTFT of this continuous waveform, but we're going to sample it at Fs prime, all right? You know where I'm going. Where I'm trying to go is to show how you can do all this digitally. But for sake of development, let's first just assume we're sampling the continuous time signal directly, and we're going to sample that at Fs prime, L times Fs. And I wrote down what the DTFT, and basically this would be the DTFT. If you think about it, x sub I of n we call equal to x sub c of n times t over L, okay? So this is the DTFT. This is x sub I of e to the j omega, see? So this is sampling it at the higher frequency. What does the DFT look like in terms of the CFT of the original signal? Well, frequency of the main version of the sampling theorem, again, always that. And what you find is that x sub I of e to the j omega. Now see, this is very interesting because it's the inverse DTFT of capital X sub, that's what we want. And look what we get. This is equal to L over T times x sub c of omega L over T, right, for minus pi less than omega less than pi. Okay? That is indeed what the DTFT, and again, of course, it's periodic outside of this interval. The DTFT of any signal, or the DTFT of any signal, is periodic. But within that interval, minus pi to pi, what you will find is that the DTFT consists of one image, looks just like the DTFT when we sampled it at Fs. The only difference is there's a different scaling factor on the amplitude and the frequency, okay? But note from the above figure that x sub c of omega L over t is 0 for omega L over t greater than omega max. In other words, I'm sampling it at this frequency. That's going to repeat, see? But the copies of it will have a big gap of zeros between the new sampling frequency and basically the bandwidth, the max bandwidth, which is matched to the old sampling frequency. See? So all of this is zeros, lots of zeros. The higher we resample it, the more zeros, lots of zeros. So let's look at this in the DTFT domain, this x sub I of e to the j omega, and what you get is this. Here is my picture, and here is the math of that, but you can see graphically that you're going to, that you're going to get a big gap of zeros. So this is just a sketch of x sub I of e to the j omega between minus pi and pi, see? So it's still going to be the shape of the, it's going to be the shape. I mean, the frequency will be scaled a little bit differently. It'll still be the triangle, which is what we're assuming for this toy example. But there will be a big gap of zeros between the pi over L, the max frequency, and the pi interval corresponding. And this, again, this corresponds to the sampling frequency, Fs prime over 2. Why? Because Fs prime is much larger than Fs. So, but the continuous Fourier transform, that's it. It's still band limited, just how it was before. It's just you really oversampled it. And yes, you will get another image way out here. 3 pi will be right here, and it will be kind of in the middle. So before, what happened was you were getting, before you see, because I made the bandwidth match to the maximum possible it could be without aliasing, before you got all these triangles and they just touched. No overlap, they just touched, okay? So it looked like that. But now, because we've dramatically oversampled it, we're getting stuff like this, see? So that is what x sub I of e to the j omega looks like. So what we've done is, in the interval minus pi to pi, we have related x sub I of e to the j omega. See, I'm going to approach this very trickily here, L over t, x sub c of omega L over t. Because unfortunately, I haven't done what I'm setting out to do, which is figure out a way of generating x sub I of n from x sub n without having to go through resampling of the continuous waveform. But this is very tricky. So what I've done is I've shown that this is true from the frequency domain version of the sampling theory. I've also showed minus pi less than omega less than pi. I've also shown that the DTFT of the original signal that was sampled at Fs, I've shown that's equal to 1 over t, x sub c of omega over t. So if you compare, for minus pi less than omega less than pi, see? So if you compare those for a while, you start to realize, you know what, x sub I, by golly, I can relate x sub I of e to the j omega to x of e to the j omega if I do something like this. I notice that implies that x sub I of e to the j, no, I'm sorry. Oops, sorry. Let me go up there. X of I, no, x of e to the, of e to the j omega L, okay, is equal to, what's that equal to? That's equal to 1 over t times x sub c of omega L over t. Jeez, that looks almost like this. Pretty dang close. All I got to do is look at this. If I multiply x of e to the j omega L, multiply it by L, what do I get? X sub I of e to the j omega. Everything's fine. So, by looking at things in the frequency domain and relating them using the frequency domain sampling theorem, with, again, no aliasing in either case, to the CFT of the continuous waveform, you have actually come up with a way of relating the DTFT of the interpolated or the upsampled signal x sub I to the DTFT of the unupsampled signal x sub e to the j omega. So That's pretty cool. We've actually come up with a way of relating the DTFTs. Now all we've got to figure out is how to relate the time domain version. So I'm going to do that, and in fact I will go back over this again. Now let's re-examine x of e to the j. So I'm going to repeat everything I just said, because some of this stuff you got to think about it several times before it sinks in, and even more times than what I talk about tonight. You'll have to rethink it. But anyway, so now let's examine e to the j omega. From the above, we know that x of e to the j omega is equal to 1 over t x sub c of omega over t. That's this, okay? And x of e to the j omega plus or minus 2 pi L, well, x of e to the j omega L is equal to x of e to the j x of e to the j omega L, okay? So x of e to the j omega times L, plus or minus even 2 pi L since it's periodic, is equal to x of e to the j omega L. So what it's saying is that if I look at x of e to the j omega L, and I replace omega with omega plus 2 pi over L, I find that I get I get a whole different thing here. Omega plus 2 pi over L times L. Well, no, it turns out I don't. The L cancels, and you get x of e to the j omega L plus j times 2 pi, which is equal to x of e to the j omega L. So what this is saying is that x of e to the j omega L as a function of omega is periodic, not with 2 pi, but actually with 2 pi over L. Okay? So what I've done here is that I want to sketch for you x of e to the j omega L. Now, why am I fascinated with x of e? Why am I focusing on x of e to the j omega L? You are because of what we talked about up here. Okay, I'm going to come back to all this, because when we did x of e to the j omega L, multiplied it by L, wow, that turned out to be x of I of e to the j omega. So I'm obsessing here with x of e to the j omega L, because ultimately I'm going to use it to get to my x of I of e to the j omega. So I'm plotting out x of e to the j omega L. Here's your triangle, but it's going to repeat at every interval 2 pi over L. See, this peak is at 0, this peak, then there will be a copy of it at 2 pi over L, and there will be, et cetera, et cetera. This will be at minus 2 pi over L. So basically, between minus pi and pi, because I've scaled the frequency by omega times L, I'm going to actually generate these closely spaced copies. In fact, if you work it out, you'll find that you will have L copies, or images, of x of e to the j omega L within the band minus pi to pi. Okay, just keep that in mind. Okay, because as it turns out, oh, there it was up there. X sub I of e to the j omega, okay, it also goes to 0 at pi over L and minus pi over L, just like x of e to the j omega, except that it has zeros between 0 at minus pi and pi. So between minus pi and pi, there's only one copy of x sub I of e to the j omega. For x of e to the j omega L, which we'd like to use to generate x sub I, it looks a lot like x sub I of e to the j omega, okay, in the sense that it has this triangle which goes to 0 at pi over L and minus pi over L, just like this did. But the difference is they're not zeros. They're just, I don't know what it is. There must be. Whew, I looked up for a second. I didn't think anybody was there. You guys are still there. Okay. I think I'm going crazy. But, how can you tell, right? In any case, so really in the frequency domain, the main difference between x sub e to the j omega L and x sub I of e to the j omega is all these extra copies, okay, of that triangle between minus pi and pi. Okay, so we kind of would like to wipe those out. And then, if we could wipe all these images out, then we would just have x sub I of e to the j omega, okay? So when I said, look, x sub I of e to the j omega is the same as L over T, x sub c of a minus, x sub c of omega L over T, that wasn't quite right, okay? That wasn't quite right. That was true for minus pi over L, less than omega, less than pi over L. It's only true in that region, okay? For all the other, for omega between minus pi and pi, no, they're not the same, because you're getting images here, you're getting zeros here, okay? So I kind of overstated, but this is the direction we're going, to try and get that. Okay, but this is not what we want for x sub I of e to the j omega. We don't want all those extra images, those copies, between pi over L and pi, okay? From here all the way out. We don't want that. Or from minus pi over L to minus pi. We don't want those copies. We want all that to be 0. So how do we make those zeros? How do we make those zeros? That's pretty easy. All we have to do is low-pass filter this. And you know what? This is a digital DTFT. We might as well low-pass filter it in the digital domain. No reason to low-pass filter it back in the continuous time domain. We'll just low-pass filter it in the discrete time domain, okay? So we don't want all those images, so we simply low-pass filter. So we're going to, let me repeat that, low-pass filter L times x of e to the j omega L. And when we do that, we will low-pass filter. Then we will finally generate x sub I of e to the j omega between minus pi and pi. Okay? So now we will have exactly what we want. We will have perfectly matched up the DTFTs. If we perfectly matched up the DTFTs, we can match up the time domain. Okay? So the problem with x of e to the j omega by itself was all these extra images that x sub I doesn't have because we've sampled it high enough. But if we can digitally low-pass filter L times x of e to the j omega, then we got it. Okay? So we simply low-pass filter to get rid of these images. We can express x sub I of e to the j omega in terms of x of e to the j omega L as follows. Very simple. X sub I of e to the j omega will equal to x of e to the j omega L. I think there should be an L there, right? X of e to the j omega L times, well, okay, never mind, I've included it in the filter, times h of e to the j omega, where h is an ideal low-pass filter. You see that? H is a low-pass filter. It has a gain, h of omega j omega at 0 frequency is equal to L, okay? And it looks like this if we were to plot it or sketch it. H of e to the j omega, this is pi, this is omega, minus pi. And what it does is it cuts off right at pi over L. Pi over L, minus pi over L, and this is L. Now, and then it goes to 0. Now, I at one point, as a student, made a comment regarding this notion. I want to just point it out. This is just minus pi to pi. This whole thing will repeat, of course, from minus in intervals of 2 pi, right? It's got to, okay? So you'll see this little function, then you'll see it again, you'll see it again. But from minus pi to pi, this is what you would see for this filter. and this value is L. Okay? So this is how, and now we have a way of exactly relating the DTFTs. If we can relate the DTFTs, we can relate the time domain waveforms without ever going back out to the continuous time world. So this is how the DTFTs of x of n and x of I of n are connected to each other. But how are they related in the discrete time domain? So that's what we want to find out. Once we've answered that question, we're done. Okay, well, first things first. If I were to tell you that y of e to the j omega is equal to h of e to the j omega times x of e to the j omega, let me say suppose. Doesn't hurt to suppose. You know, hey, I typically don't suppose much. My boss does the supposing for me, but I'll give it a shot here. Let's suppose y was this. Now, how do we relate y of n? Well, we know how that's done. That's just h convolved with x, okay? So we know that relationship. So that was a suppose. But here our question's a little bit different. Here we have h of e to the j omega times x of e to the j omega L. And how does that relate to x of I of n? See, all in the time domain. How does that relate back to the time domain? Well, to answer that question, the first thing you got to figure out, if our DTFT was of the form x, what does that correspond to in the time domain? See, that's the first question. Now, and I don't expect you to do this, but if you think back to that sample homework set that I give you before the midterm, and I think I made a mistake on that, the key to this is kind of there to some extent. But anyway, well, first of all, let's look at something called a rate expander. That's a good one. And in fact, I'd give you an example of that in that sample homework set. A rate expander. Okay, what is a rate expander? It's very simple, and I want you to keep this in mind because you will see it over and over again. A rate expander is a box with an arrow going up an L. That's your rate expander. So we're done. We just did it. No. What is a rate expander? Okay, what it is this in the time domain, or that. Okay, it is. I also call it a zero stuffer. Okay, a zero stuffer. And basically what it does is, do I have a picture of it? No, I didn't. But anyway, so I will call this x sub e of n. This is my rate expander. Okay, and what it is this, call this sample, I'll call that x of 0. And then you go over here. This is n. Go over here, L samples, n equal L. Guess what you get? That's, guess what? Oh, this is, yeah, x of 0. That point is x of 1. See? And then you have a bunch of zeros, and then n equal 2L, and you get x of 2. Okay. So basically what a rate expander does is it takes your input and it kind of like increases the sample rate by just inserting a bunch of zeros. So if you had, say, an FPGA or anything, and you were clocking these samples originally, x of 0, x of 1, x of 2, you were clocking those every t seconds. When you build this rate expander, you have to use a different clock. So this clock this maps to 1 over t. Okay, or well, I really should say t. This would be 2t, and so on. But these little clock pulses would have to be at t over L, 2t over L, and so on. So in other words, if you want to, in hardware, if you really want to build a rate expander, first of all, you have to use a clock that's L times faster than your original clock that you sampled the data with, and then that new clock, you start running the data in, and when you don't have, because you only get data every L ticks of that fast clock, what do? You just put zeros in there, see? So it's data that I have, 0, 0, 0, data that I have, 0, 0, 0, data that I have, and so on. That is a rate expander. What does it look like mathematically? Here it is. In fact, the simplest version is x sub e of n is equal to summation. What do I want to use for my index? Xk equal minus infinity to infinity. I will let you convince yourself that this is true, x of n minus k times L. That is the time domain mathematical form for the rate expander, okay, in terms of a delta function. It's very simple. And you should convince yourself, oh yeah, he's right. Because here you get samples, you actually get zeros most of the time, but whenever n is equal to KL, bingo, you get the x of k value, see? That is the rate expander. That's what this little box arrow up and L means. It means basically stuffing L zeros or L minus 1 zeros between samples of the data that you have. Okay, so, yes?
What is it used for?
That's like that song by the group called War. War, what is it good for? There was a Seinfeld episode where Jerry had, I'm going to answer your question, don't worry, where Jerry had told Elaine that she was supposed to meet this author, a Russian author, and they got talking about War and Peace, and she said, you know, it's interesting. War and Peace was originally entitled War, What Is It Good For? But which is you probably wouldn't know this, but that's the name of this pop song from 20, 30 years ago. But anyway, she got in trouble doing it too, because the guy knew that was all crap. But in any case, okay, so what is it good for? To answer that question, let's look at the DTFT of this thing. Okay, what's that equal? Well, let's work it out. It turns out it's in this version, it's pretty simple to see. Okay, so x of e to the j omega is summation n equal minus infinity of x of e of n. Go through its step, but x of e of n is the summation thing with that delta. Move the summation signs around, and you get this, and look at this. This looks like, that looks like the summation n equal minus infinity of delta of n minus kl. That's just going to be equal to e to the minus j omega k times L. So you end up with this sum, k equal minus infinity, nothing up my sleeves, I have no sleeves, minus infinity to x of k e to the minus, what is that? What is that? Well, by golly, that is x of e to the j omega L. That's what we wanted. That's what we wanted. So when I said, how does x of e to the j omega L relate to x of n, question mark, we just answered it. We did it. We figured it out. Okay, so what is the time domain representation of x of e to the j omega L? It's a rate expander. It's these samples of x of n with a bunch of zeros stuffed in between. So that is just a handy-dandy way of generating x of e to the j omega L, and therefore is a handy-dandy way of generating our upsampled waveform. This is exactly what we need to generate our upsampled waveform x of I of n. So the complete digital upsampling system from rate f sub s to rate f sub s prime equal L times, that's it. That's what it's used for right there. So this is an interpolator or an upsampling system. X of n goes in, it goes into this rate expander. Now again, to implement the rate expander, so your sample rate here, you're clocking your FPGA or however you're implementing this at frequency fs. In here you have to be clocking it at LFS. And when you don't have a sample for x of n, you just put a 0 in there. until you get a new sample of x of n. L clock ticks later, see? So that's what this rate expander is doing. It's pulling out the samples of x of n when it doesn't have a sample because its clock is running L times faster. It just puts a 0 until you get until n is some multiple of L, and then I'll put in the next sample. So that's how that works, and that gives you in the frequency domain x of e to the j omega L. And then the only thing left is, and you remember that had all the images, so it's low pass filter it. That's what that does. And you know what you end up with? X of I of n. And it's all done in the time domain. You didn't have to go back to into the continuous time, ugly world of continuous time, as we will learn. And you did the whole thing digitally. All digital upsampler. Or we call it resampler. That's what MATLAB calls it. Okay? And that's pretty much it. So how would you do this in MATLAB? You say, well, use resample. You just said, yeah, you can do it. But here, look, in MATLAB, what you would do is you're given an array, x, okay? Now, what you're going to do is create x e equals, let's put a bunch of zeros in, and how many zeros we will have, that will be L times the length of our array x, see? Semicolon, don't forget that. Okay? So I start with an array x of some length, and I will create a new array, which are all zeros at this point, and then, you know what I'm going to do? I'm going to, my next line, x of e of 1, L, end, that's just the end of the array, that will equal x. So help me, it'll work. It will work because you created an array that's L times longer, okay? Then what you do is you take your low-pass filter. Now, to do it exactly, you need an ideal low-pass filter. Now, we should all know now there is no such thing. We can't have, but any good low-pass filter would work as long as its cutoff is near this pi over L. And so there you go. X sub, I call it xi is equal to filter say it's an FIR filter, 1, x sub e. Voila, done, the end. That's exactly what the resample function in MATLAB does. So it's a very handy-dandy way of generating samples at a much higher frequency or a different sampling frequency, all in the digital domain. So that is upsampling. That's its base. So I encourage you to read through these notes, not only just for the course, but there may come a time when you need, if you haven't done it already, where you need to do upsampling. That's how you do it, and that's what the MATLAB resample form or the resample routine does, and I strongly encourage you to use that. Downsampling, okay, I guess we're going to take a break here. I'm almost ready. Okay, well, no, I can finish this real quick. Downsampling is actually much simpler in the time domain, because there what you're trying to do is you're trying to generate samples of x sub c of nt prime, where t prime is equal to L times t, okay? T prime is equal. So this is just x sub c of n times L times t. Well, guess what? That's just equal to x of n times L, okay? So if you've sampled the input at samples x of n, and you want to generate the downsample, that's pretty simple. You don't have to do this other thing. All you have to do is just subsample it, okay? But not quite done. There's a potential problem here. There is a potential problem. Oh, and by the way, this is the symbol we use. So the upsample, where we do that rate expander thing, was an up arrow in L. This subsampling operation is denoted by downsample in L, okay? But there is a little problem, and the problem is, if this is not aliased, okay, because we've sampled it at Fs, this may be, because this is sampled at Fs prime equal Fs over L. For upsampling, there was no problem, because we're going to resample it to a higher rate. In downsampling, potential problem, because just because you didn't have any aliasing when you originally sampled the signal doesn't mean you wouldn't have any aliasing now if you sampled it at a lower frequency. So you kind of have to worry about that. So what people do, and when you start to look at, this is kind of the inverse image of the upsampling. So what you do is you take X of n and you low-pass filter it. You low-pass filter it, and this low-pass filter is like minus pi over L to pi over L. And what that does is it keeps it so there will be no aliasing when you subsample it here. So this is the picture for downsampling. And if you compare it with upsampling, it's almost like kind of the mirror inverse. In upsampling, there's this rate expander, and then there's a filter. For downsampling, the filter comes first, and then there's a downsample or subsampling operation. So that is downsampling. I told you it was much simpler. Now the frequency domain, though, remember the frequency domain, the rate expander was just x of e to the j omega L. In the frequency domain, the downsample DTFT, after downsampling, is a little more complicated. And that's Mitra discusses that, so I won't go into the derivation of that. But that is the DTFT relationship. So in the time domain, or in the discrete-time domain, you know, x sub d of n is x of nl. It's pretty simple, but in the DTFT domain, it's a little more complicated, and x. Anyway, that's the DTFT relationship. And in fact, you say, hey, wait a minute, there's L comp. This looks familiar. Yeah, this is kind of like what happened when we did the frequency domain version of the sampling theorem, except everything now is in the discrete world. But it kind of looks like that. You get copies of this, and the copies are because you could be aliasing. So that's why you put this low-pass filter, and then everything's fine. So that's that. The final question is, what if, okay, let me go further. I've gone this far. Let's go a little further. Now what I want to do is generate samples at a rational relationship of the old sample rate, n times m times t over L. How can I do that? And you answer resample. Use the MATLAB function. Yeah, you're right. That would do it. But what the resample formula would do is this. It will upsample first. Okay, you don't want to downsample because you'll get rid of information by either aliasing or low-pass filtering. So upsample first. That's that little box with the arrow up. Low-pass filter that. You would low-pass filter that at pi over L. And then you take that, now that's your x sub I of n, and then you low-pass filter that at pi over m. And then you go to the subsampling, and voila, you got it. Okay? So you kind of combine those two together, and you do it in this order because you upsample first. And then, if you're even more clever, you realize, wait a minute, this is a filter. I'll just cascade those two filters together and make it one low pass. So this is kind of it. The cutoff is the minimum of pi over L and pi over M. So you just build one big low-pass filter, and you sandwich it between an upsample and a subsampler. That's it. So that are my notes on sampling. Why don't we take our break, and I will see you in 15 or thereabouts.
sending an email. Everything's okay. How you doing?
Tired, man. I've been here all day.
Oh yeah?
Yeah. I'm gonna have another class at 8 in the morning
What?
at like 8:30.
Which
Not-
class?
I mean, not 8, but 9.
Which class?
That's the mobile. It's a mobile class. It's called mobile.
Mobile?
Yeah, mobile for mobile class. This is I can't be doing something this morning here. It's a EE 553.
Mm-hmm.
I'm sorry, 532. 532.
EE 532.
Yeah, it's 532. It's unbelievable. It's a class we have mobile. Wireless internet and persuasive computing.
Huh?
Oh, wireless internet.
Oh,
So it's about mobile devices.
I see. How do you like it?
Yeah, I mean, it's a good professor. He's a good
Mm.
professor. I didn't realize how much. I really need to go sleep early today.
Yeah.
I went to sleep last night and I got about 3.
Oh man.
So I thought I was all off, now I'm still young, I can do it.
I can do it. That's the spirit, Carl. Yeah.
It's not posted yet.
I think it's posted yet. Yeah, already.
Already?
Yeah.
When?
I don't know. I checked it yesterday.
Yesterday, and it was posted.
It was already posted.
In, on demo
And
website.
then, yeah.
Wow.
Mm-hmm.
I didn't say it. Okay.
When did you check it?
Oh, okay. Okay. I guess I checked the wrong folder. Yeah.
It's under
The
assignment.
yeah. I missed that.
Yeah.
It's
yeah.
due on.
The 16th, so next week,
Oh,
next Wednesday.
I got it. Thank you.
It looks like a short one,
Oh, sure.
like 4 or 5 exercises.
Okay.
I'm not sure. Yeah, no problem.
Thank you for the reminder.
kind of get out there for a while, you know. Okay, so I just want to point out we did cover a lot of ground, so in those notes. So the second, the homework set that's posted is a good place to practice for that stuff because it covers all the notes we just went through on sampling. What I'm going to talk about now, so please review that material. Start to feel comfortable with it. Hopefully the homework will help. So what I'm going to talk about now is, I'm still going to talk about sampling, but I'm going to kind of, I'm going to, just a second, I'm going to look at something. Yes. Yeah, I'm going to move on to a kind of a second topic, the follow-up topic on sampling. Now, these notes that I'll talk about tonight, or the rest of the lecture, are a separate set of course notes that, of course, have been posted, and it's sampling part 5-1, sampling.5-1. And it's sort of the next, sort of the secondary, or this, I shouldn't say secondary, the second topic, a kind of a more advanced topic. That's the word I'm looking for. It's a little more advanced topic and way of looking at sampling, and especially ways of implementing resamplers and ways of doing frequency channelization. So there'll be some interesting stuff here. Most of this is in Mitra, and I think it's maybe it's 4th edition, section 13.4. It's either the 3rd or the 4th of Mitra. So, but anyway, it's just basically on sampling, and we're going to talk about, in fact, we're going to talk about a couple more topics of sampling. One is bandpass sampling, which kind of a deliberate way of aliasing, or it's what I would call aliasing on purpose, and I'll talk about that later on. But for tonight, or the rest of the lecture, I'll talk about something called polyphase filters. Polyphase filters, what are they? How are they related to sampling? What are they used for? And typically what this topic, or this range of topics will cover, is basically more advanced ways of implementing samplers and resamplers. So, and it uses all the basic properties that we know. First up, before we even get started in detail, I want to talk about a key relationship, which is critical to our, very important for our understanding of these different sampling techniques. And like I said, this is the more advanced topics in sampling. In fact, if you recall, yeah, let's take a look at these blocks before. Look at this. Well, anyway, let's look at this one. We'll look at the other one too. Now, if you look at this, and you are all of a sudden an FPGA programmer or a software programmer, and you look at this picture, this is a downsampler, and as I said, you have to filter first to get rid of or prevent aliasing, and then you subsample. What is wrong with this picture? If you look at it from the perspective of an implementer, somebody who's going to actually build this in hardware or software, well, the thing that's kind of wrong about this is that what is the sample rate here? It's F sub S. What is the sample rate over here? It's F sub S over L, see? And that gets done right in here. So what is, because you're just grabbing every Lth sample, so you can use your input clock is at Fs. You can run this with a clock at Fs divided by whatever L is, and it'll just grab every Lth sample. Now you say, well, but what happens with samples it misses? Well, it just misses them. Too bad. Oh well. It loses a lot of samples, but it grabs every nth sample. What is wrong with this picture is that rhetorical question. Is anybody? No. Well, if you think about it for a while. If you did think about it, the one thing is that you see this filter? You're going to implement that filter. Now, what is the filter? Well, for the heck of it, let's say it's an FIR filter. Let's say it has L taps. Or no, that's not a good word. Let's say it has M taps. So the one thing that's wrong with this picture is that you have to do the operations to implement this filter. And as we'll talk about later, this requires M adds and M multiplies to produce every single output, okay? What is wrong with this picture is that you're doing this at the sample rate Fs, see? That's the high sample rate. Wouldn't it be great if you could do these type of operations at the sample rate Fs over L? That's the low sample rate. Lower sample rate, the better it is. The lower you can clock an FPGA or whatever your algorithm that you're implementing, the lower you can clock it, the better off you are. You meet timing, you meet all that stuff. The picture here, though, is if you just did this direct implementation, you have to do the hard work. This is the hard work, the filtering operations at the very high rate. And if you think about it, and you look back at the block diagram for upsampling, you got the same damn thing. This is sample rate Fs. Over here is sample rate Fs times L. So this is low rate now, and this is high rate. And once again, you're doing your filtering operations at the high rate. That's what's wrong with that picture. But it's obviously, it appears to be a necessity because that's how the processing comes out. This is used to get rid of images after you've upsampled it. This filter is used to prevent aliasing, getting rid of high frequency components before you subsample it. So how can you get around this? Well, I will tell you. This is the point of these so-called polyphase filters. They have some very interesting applications. Okay, so to get to that, where we can actually reverse our operations to the lower rate, we start with two, actually two, but this is a very, very important identity. This is identity 1. There's a comparable one, and I'll point it out in just a second. And identity 1 says this. We have a signal, and we subsample it. Okay, remember, this is x of n times m. And then we filter it. Well, guess what? That's equivalent, and we're filtering this at the low rate. So this is high rate, this is low rate, okay? So here the filtering is done at the low rate. This is equivalent to taking our input, feeding it into a filter at the high rate, okay, and then subsampling it down to the low rate. So basically, if we can reverse this picture, here we have a high rate and filter, and then we go down to the low rate. That's what we want to do. Or, I'm sorry, no, that isn't what we want. That's what we have. Filter, subsample, okay? So filter at the high rate, subsample at the low rate. But that is equivalent to taking the data, first subsampling it, reducing it to the low rate, Fs over m, and then doing our filtering operations. We like A. This has a very nice implementation. B, not so much. That was the picture we drew for our subsample, or downsampler, okay? It kind of looked like this. But if you stare at this picture for a while, you will notice something, though, that doesn't not quite right. I didn't just flip around the subsampling and the filtering. I did another operation. And if you watch it, look at it too quickly, you'll miss that. You know what I did? See that filter? This filter is different. This is H prime of Z. If you look at it closely, it's related to H of Z, but it's through that You know, remember that old relationship? H of z to the m, which is how we derive these comb filters and so on. In other words, it is a frequency scale version of the filter used here. So what this identity is saying is if you have a filter, h of z, and you're doing it at the low rate, it would be equivalent to filtering at the high rate as long as that filter is related to this filter by that frequency transformation, z replaced with c to the m. Okay? Now you think, oh, geez, that isn't quite what we want to do. I don't see how that's going to help us. Patience, patience. We will see how it's going to help us later on. Okay, but first of all, let's just see if this is true. And here I have a couple of, well, first of all, an example, just to kind of get your feeling, yeah, maybe it is true. Okay, suppose h of z looks like this. H is equal to, so this is an example. H is equal to 1 plus the inverse. And what is h of n? H of n is equal to delta of n plus delta of n minus 1. Basically, it takes the signal and it shifts it or delays it by one sample and adds it to the original signal, and that's the output. Okay? So that is that. What about h prime of z? What about h of z to the m? What's that look like? That's 1 plus z to the minus m. And what is the impulse response of that? It's just delta of n plus delta of n minus m. So those are your two filters. So that takes care of these guys. So what is the output? Well, first of all, what is x sub d of what is x sub d of n? In all cases, x sub d of n, and for structure A, well, in structure A, x sub d of n is just x of n times big M, okay? What is y of n? Y of n is h convolved with x sub d, and that's pretty simple. In this case, that is x sub d of n plus x sub d of n minus 1. Or if we want to put that back in terms of x, that's x of n. I'm rewriting the same thing I've typed, except I can read it better. So I'm following. Plus x of n m minus m. Remember, whenever you have something like this, you replace n with n minus 1. And so you would replace the n here with n minus 1. You end up with that. Now, let's go to structure B. Structure B is that we take xd prime of n, and before we downsample it, we filter it with h of z to the m. So you get this result. So this is going to equal x of n plus x of n minus m. Remember, this is delta, in the time domain, this is delta of n plus delta of n minus m. And then you downsample that, so what do you get? You get x of n m, right? Plus, you replace little n with little n times m, plus x of n m minus m, and lo and behold, it's the same as a. So that kind of gives you some kind of a warm fuzzy that, yeah, maybe this is right. But that's a special case. Now, in general, I forgot the number. In general, you use this relationship, which I, of course, didn't prove, but this is it's the old book. Mitra. This is pages 7.4, and that's the most recent edition, 7.4. I get confused with these editions. I don't know why he wrote a new edition. This thing is big enough as it is. But anyway, he's just confusing me. But anyway, in Mitra's book, he talks about this, and I didn't prove it, so maybe I'll have a homework exercise with this. But it's probably wise that you at least look at Mitra and see how he derived this. I have a different way to derive it than he did. Maybe I'll mention that later on. Anyway, okay, so for structure A, we first of all take x of n and subsample it to get x sub d of n. So let's go right to the, for A, yeah. So let's go right to the frequency domain. So y y of e to the j omega, what's that equal to? That's equal to h times the dtft of x sub d, but the dtft of x sub d is this. That's x sub d of e to the j omega. And that was that relationship I mentioned but didn't prove. But a bing right here. And you substitute that in, and you get this result. Now, what about for part B? Well, you're going to use this formula again, but here, y of e to the j omega is going to be 1 over m. So this is x sub, what I'm calling x sub d prime of e to the j omega. That's the signal right here. But x sub d prime of e to the j omega is equal to x sub e to the j omega times h of e to the j omega times m. Don't forget the m, okay? So you plug that in, and you use your formula for x sub d of e to the, or I'm sorry, you use the formula for the DTFT of the subsampler. That's this, right? Oh, that's, no, forget that. That's just the formula. So that's the formula for the output of the subsampler in terms of the DTFT of xd prime. And x sub d prime looks like this, because it's just x times e to the j, or h of e to the j omega m. You put it all together, and you find that for structure B, you get this, y of e to the j omega, summation, I won't rewrite all this again, this formula, x sub d prime, e to the j omega, I have to look at this very close to my eyes, e to the j omega minus 2 pi k over m, and then you substitute in for x sub d prime of e to the j omega equals, what does that equal? X sub d is equal to h of e to the j omega m times x of e to the j omega. Anyway, you substitute that all into here, you get this, and after it's all said and done, you end up with this result in the frequency domain, which turns out to be equivalent to what you showed for y of e to the j omega for system A. So the so I encourage you to go take a look at this. The two DTFTs are the same, so therefore the two systems must be equivalent. So what it's saying is that subsampling and then filtering, which is what we'd like to do, is equivalent to filtering and then subsampling, provided the filters are related like this. Okay, that's the first important relationship. One. Here's the second one, and I will let you. You also can show this in the frequency domain. Actually, it's a little bit simpler to show this because you don't have that funny, goofy formula for the DTFT of the output of a subsampler. But you can go through, and you should, and it's also in Mitra, and you find that these two systems are equivalent. Namely, upsampling and then filtering at the high rate is equivalent to filtering and then upsampling. So here you do the filtering at the low rate, and here you do the filtering at the high rate, provided that the filters are again related by this frequency transformation. So this is h of z to the L equals h prime of z, let's call it, and this is h of z, okay? And it's the same type of argument, except it's a little bit simpler because the formulas for the upsampler are a little bit simpler. So this means that linear filtering and down or upsampling can be interchanged, provided, that's the big one, we modify the linear filter. H prime of z is h of z to the m. This is a very important result, which leads to important simplifications of up or down samplers. That's what I'm telling you. This is the more advanced sampling topics, digital resampling topics. Okay, so let's look at a filter system function in a in a brand new way. That's it's also Mitra section 13.4. 13.4. chapter 13 is Mitra. Mitra, very interesting. He did a lot of work on resampling systems using these so-called polyphase filters. So he's got a nice treatment of that. Now, by the way, I just to remind you, I talked about two important identities, which you can really prove in the frequency domain in both cases. This has nothing to do with polyphase filters. We're going to come back. We're going to get to polyphase filters right now, but this is just kind of an aside. This is a preliminary type of result that I want you to start thinking in terms of these two systems. And now we're going to put it all together. But step 2 is to discuss what polyphase filters are and polyphase decompositions and all that jazz, okay? Here is, in a nutshell, a polyphase, what I will call a polyphase decomposition. Polyphase decomposition. And in a sense, it's pretty easy. It's just recounting is all it is. Okay, polyphase decomposition. Start with a filter, impulse response. And I will call that, for reasons that will be clear in a few minutes, hopefully, a prototype filter. We will start with the prototype because I'm going to make variations on it. And let's call the impulse response to that prototype filter H of n, okay? Now what I'm going to do is I'm going to recount a little. I'm going to count a little bit differently. I can count as n, where n is generally minus infinity less than n less than infinity. It better be positive if you have a causal filter, of course, and it better be finite if it's an FIR filter, okay? Now what I'm going to do, and it's really this simple, is I'm going to think of n. I'm going to break up n as follows. I'm going to write n as, or I'm going to write any integer. Let's call it any integer. What do you want to call it? We'll call it k. Can be written as n times L plus k. This is just another way of writing an integer. What is L? L is some integer. L is some integer greater than or equal to, well, yeah, let's make it greater than or equal to 2. What is k? K is between 0 less than equal to L minus 1. So suppose L were 2. And you wanted k, and k also runs between minus infinity to infinity. Okay, so let's say L was 2, and you wanted k to be 3. Okay, how would you do that? Well, you would pick L as 2, you would pick little n as 1, and k is 1. K is between, if L is 2, k is between 0 and 1. So if I wanted k to be 3, I would, and L over 2, I would pick n of 1, k of 1, and so on. Any integer, you can make NL plus k any integer you want, depending on your depending on your choice of n and k for a given L. But k has to always between 0 and L minus 1. So anyway, that's just a way of writing things. Okay, so I'm going to define, this is my prototype filter H of n. I'm going to define a new filter with impulse response E sub k of n, and I will write that as H of n times L for some integer L greater than, oh shoot, I'm cutting into that. I'm going to write that again down here. E sub k of, and then I always copy all of these things in the type version anyway, so this is probably confusing, but oh well. H of n times L plus k. Again, 0 less than or equal to k, less than or equal to L minus 1. So I will call, define E sub k of n to be H of nL plus k. And, yeah, so in any case, that is the definition. This, by the way, is called a polyphase decomposition of my original filter H. And it's called polyphase because it spans the original filter for as long as you increment for each value. If you let k go between 0 and L minus 1, k is like a shift or time shift, that will get to all the points in the original filter H of n. Let me go a little further, and at some point it'll start to become clear. Sometimes I don't explain this the best way. Oh, well, you know what? Yeah, okay, let me just say this, and then I'll go back to the type part. Let's say I wanted to look at the z transform, H of z. Okay, what's that equal to? We know that's n, H of n, z the minus n, right? But I can rewrite this as a double sum from summation k equal minus infinity to infinity. That's also the range this goes to infinity. I can write this as a double sum, and I'll write an inner sum. Well, that's all right. P, I'm redefining these things, but all right. L minus 1 of H sub k times L plus P times z to the minus KL plus P. Now, I want you to look at this, and you study it, and you need to convince yourself, yeah, these two are the same, see? Because I can point, this is the original z transform, this is the definition. But I can tell you, any term in this sum is going to be a term in this sum for some P and K. And I apologize, I've kind of redefined the E sub K. I'm not calling it E sub P. I should. That's all right. That's all right. Anyway, so these two terms are, or these two transforms are the same. Any term in this sum from minus n minus infinity to infinity is going to be also a term in this double sum for some P and K, okay? Depending on what L is. If L is different than P and K, it will be different, but you can still, every term in this sum will be a term up here, okay? So now with that, without further ado, now we can write this out. So H of z is summation H of n, z to the minus n. That can be written as summation k. This is going to be E naught of k of H of KL. That's sort of like this with k equals 0 times z to the minus KL plus summation k, H of KL plus 1, that's E sub 1 of k times c to the minus KL plus 1, and so on. And if you look at this, this is equivalent to that double sum, see? I've just expanded the inner sum out. K times summation, well, P equals 0 to L minus 1, H of k times L plus P times z to the minus KL plus P. Okay? These two are obviously the same because all I've done is I've just expanded the inner sum, and that's why you get all these different terms. But I contend that any term in this infinite sum over n from minus infinity to infinity is represented in this sum, in this double sum, for an appropriate k, depending on, I can always pick a k and a p such that that particular term will map to a term here. There's no more terms, there's no less terms. And that follows all because I can write I can decompose any integer, I can decompose as, or I can write it as k times L plus P. I'm switching things around. But I can write any integer in terms of this relationship, any integer, as long as this term here is between 0 and L minus 1. That covers all the integers. So it's just a different way of writing the sums. Okay? So that is what is called the polyphase decomposition of my original filter. Thus, we can decompose any h of z as long as we have an impulse response, and the impulse response can be infinite. So this type of decomposition would work for either IIR or finite impulse response filters. Either one can be written. We can use a decomposition for this. Thus, we can decompose any h of z as follows. H of z is equal to E sub k of z. Oh, this is just a handy-dandy way of writing it. H of z, I can write as summation k equals 0 to L, and these indices are dummy indices, but I'm using all different types, and I really apologize between my handwritten notes and the notes here. Z to the L times Z to the minus K. Okay, so I can rewrite this double sum in terms of this handy formula. The second sum is in here. EK sub Z is equal to the Z transform of each of those components. E sub K of n times Z to the minus n. Okay? So I can write it like that. This double sum, how does it look like this? Because if you let E sub K of Z to the L looks like summation n E sub K of n times C to the minus n times L, and you start to see that and that's going to be the outer sum, and then the inner sum is this one, this writing on this. So you can look at those two are equivalent. Okay, so this is just another representation, what I've written here, for the double sum. Thus, we can decompose any h of z as follows. Okay, this, which is equivalent to this. Okay, so that's just a little background into the. Please take a look at that. And any questions, let me know. We can talk about that. What I would encourage you to do is to convince yourself first and foremost that those two representations are equivalent. The double sum and the single. Oh no. The double sum and the single sum. Those are two equivalent representations. Let's look at a block diagram of this. That always helps. One picture, you know, that thing. So here's a block diagram. Here is my x of n, and I go into filter E naught of z to the L, okay, where the E sub k's of z to the L are defined here, all right? And then that goes out. Now I take the x of n and I delay it by one sample. This is x of n minus 1, and that goes into this filter, E1 of z to the L. And so on and so forth. I take this and delay it in. And that y of n, if I looked at y of z would equal x of z times h of z, where h of z is equal to k equals 0 to L minus 1 of E sub k of z to the L times z to the minus k. There's not much there. I mean, that's clearly how I'm expanding. I mean, you can see the block diagram. The z to the minus k correspond to these delays, and the E sub k of z are these components. Okay? So that's all I've done. And I've defined the E sub k of z's, again, are the z transform of each of the components of h of n, the little e sub k of n. Okay, where little e of k of n, that impulse response, is h of nl plus k. So a lot of things you're seeing. I mean, it's all defined and it all works out, but there's a lot of little pieces that we're trying to put together here. Okay, this is called then we can generate y of n with the following polyphase decomposition. It's called polyphase because you're essentially breaking up x of n into various delayed versions of x of n. X of n minus 1, x of n minus 2. Those are called the polyphase components of x of n. Okay? So this whole structure which is, here's the block diagram, is called a polyphase decomposition of the original filter. So we're taking that, so basically this is equivalent to X, H, Y. Okay, those two are equivalent. Okay, X, H, Y. I know what you're thinking. I can read minds. Here's what you're thinking. I know. You're thinking, what the hell are you doing? You've taken something which is trivial and made it this. Well, how's this going to help us? How's all this seemingly more complexity going to help us? Well, I'll tell you where it's going to help us. It's going to help us when we want to do downsampling, okay? When we're ready to do... Uh-oh. No, yes.
Sorry about that.
No, don't worry.
Sorry about the
We're so crowded in here.
we took some chairs.
Full house, yeah.
That's fine. You could actually have left them outside. All right. Thank you. Anyway, so seemingly I've made the problem more complicated. I've taken a simple block diagram and expanded it. How's that going to help us? Here's where it's going to help. It's going to help if we want to do downsampling. Okay? We're going to put a couple things together here. I have a couple more minutes, okay? So here's what now suppose we want to implement a downsampler. Gosh dang it, Mitra. That's, gosh dang it, 13.4. Suppose I want to implement a downsampler. Okay, remember the downsampler? Okay? X goes into the filter, I'll call that anti-aliasing filter. It's a low-pass filter. Okay, that's the anti-aliasing filter. And then I'm going to subsample. Okay, that's what I'm going to do. Now, I want to implement that. You know what I'm going to do? You know what I'm going to do? I'm going to replace H of Z with this structure right here. And you say, hey, I got a question before you do that. What are you going to pick L? You said this L was arbitrary, so you're going to do this. First of all, what are you going to choose for L? I'm going to let L equal to M. Let's take a look at this. Let's see what we got. Okay. The first thing I want you to realize, which we talked about in linear systems, if I have a system, X subsample M and output Y, and I ask you the question, is this system causal? No, probably not, because it's Y is equal to X of M times N. Is the system time invariant? No, it's not time invariant. But is it linear? Yes, it is linear. This is a linear system. Okay? What that means is that, well, here you'll see. Well, what it means is that if and I'm going to put the downsampler, the subsampler here, I could just as well move it to each one of these paths, and I'll get the same result. So let's take a look. Then we replace H of Z. Okay, so again, here's our picture. X, H, downsample, M. Okay? So what we're going to do is we're going to replace this with the polyphase decomposition. We're going to pick L equal to M. And we're going to move the downsample operations to each of these paths. Okay? So here's what our downsampler will look like. Then we replace H with its polyphase decomposition, and we observe that downsampling is a linear operation. Then we get the following block equivalent. So this block diagram, it's equivalent to this. Now you're still going to say, yeah, okay, fine. Maybe that's true, but it's still a more complicated system. I still don't see what the gain is by doing this polyphase decomposition. But let's take a look at this polyphase decomposition. These are each of the polyphase components. Remember, right? E sub k of n is the same as ek of z. Okay, the polyphase decomponent of the filter itself. Okay. So let's take a look at each of these filters. E naught Z to the mth, capital E, that's the Z transform, downsample. E1, Z to the mth, downsample. E sub m minus 1, Z to the mth, downsample. What did we learn earlier? Let's kind of put everything together. And recall now, this is, even though I delay it, this is still high rate. See? All of these filtering operations are done at the high rate. It's not till we cross this boundary that we go to the low rate. Okay? Everything here is high rate. But we're not quite done. Let's think back to those identities we proved before, A and B. We can now use the above equivalence, that was equivalence 1, which says that if you have this configuration, filter of the form Z to the m, downsample m, hey, you know what? That's equivalent to downsample first and then filter with E sub k of z, not Z to the m. So here is, so we're going to take this block diagram. Using those identities, we're going to end up with this block diagram. Okay? So now you're probably thinking, well, you got all these branches. You sure this is going to be easier than just doing the regular brute force downsampling? And the answer is yes, it is. And first of all, here's what it looks like. So now we have our polyphase by delaying each of these paths. This is still high rate. Right here is high rate. But now look, everything after this is low rate, including the filtering. So now you're doing the filter. This is mathematically equivalent to the downsampler, okay, the original downsampler. So this is mathematically equivalent to this H, and then go to the low rate. See? What am I calling? M. All right? This is mathematically equivalent. But now all the filtering operations are being done at the low rate. If this data is coming in at Fs, this is Fs over M. We have used this in software-defined radios that are flying right over Mars right now. The Mars Reconnaissance Orbiter is based on this type of architecture for doing the front-end sampling. So what is the big deal? Why is the Mars Orbiter interested in this? Well, the Mars Orbiter, its electronic package is very limited in processing power. So anytime you can reduce something and make it run slower, we like that. So what is the big deal about this? Well, now all the filtering functions are done after the subsampler and done thus at a much lower rate. You will agree with me on that. The length of the filters, the E sub k of z, remember, E k of z is little ek of n. What is little ek of n? That's equal to h. This is what I call the prototype type. It's of almost done.
Pardon me, Professor, 5 minutes remaining.
Okay, 5 minutes. 5 minutes. Give me 5 minutes, I'll give you the world. No, that's equal to this. Look at what's going on. If the length of h of n is some length, then look, you're picking every mth sample. The E sub k of n is like, this is like 1 over m times length. So the length of ek is like 1 over m times the length of h. Okay? So that's nice. The length, number 2, the length of the filters, ek of z or ek of n, is a factor of 1 over m smaller than the original filters, and thus they are generally much less complex. So that's pretty cute. Not only do you have to implement those at a lower rate, which is nice, they're also smaller by a factor of m than the original filters. So the new polyphase decimation structure can be implemented at a much lower sampling rate, which in turn means less power. And I did a little example, I only have 3 minutes now, of processing reduction with this new structure. Suppose H of Z, our anti-aliasing filter for downsampling, has 100 coefficients. It's a 100 coefficient FIR filter. let's say the input sampling rate is 10 megahertz, and the desired output rate is 1 megahertz. So in other words, m is equal to 10. That's our downsampling factor. In the direct implementation, this would require 2 in operations, and adds and multiplies to implement the prototype filter, which has 100 coefficients, and you got to do that for each input sample at 10 megahertz. So that would require a processor running at 2 gigaflops. But with the polyphase implementation, and 2 gigaflops, well, today that's not bad, but that's a lot of operations. Check this out. The polyphase filter, when I worked it all out, would run at about a tenth of that, 200 megaflops. So you've got to factor. So even though you did all the work of having to split this thing out and seemingly do a much more complicated architecture, the end result is worth the gain in doing that. Especially if you're speed limited, okay? So that's what I will say now. And by the way, if we wanted to do that was downsampling. If we wanted to do upsampling, there is an equivalent architecture to do that, and guess what? It looks like this, okay? All based on the polyphase decomposition. So I'm sure I'm out of time now. Let's stop here. We'll take up next time. But again, like I said, for homework number 4, or whatever it is, I guess it's number 4, just review the notes that I did on sampling. This is what I'm calling sampling part 2. Just review carefully, make sure you understand the notes on sampling. The sampling notes. So I'm doing 5-1. Just study 5, go through the lecture notes. That will help you do the homework set number 4. Once you've done that, then we can talk about polyphase. Okie doke. I will see you all next week. Hopefully I will have your projects graded and you will all get